So we'll start in a minute for a while. Is that fine?
Yeah, sure.
I will probably wait for a minute or two,
Hmm.
just in case people. That's the
Yeah, wait
error.
for a minute.
That's the error bar for clocks.
Yeah, maybe we can start, Ashish.
Okay.
Yeah, can you share your screen?
Yeah.
Yeah, we can see.
So today we are going to discuss another experiment, which is the sea surface experiment, a sea surface interferometer, and you will see why it is called a sea surface interferometer. Uh, so interferometry is a technique used in radio astronomy for imaging the source or getting some resolution, angular resolution information about the source. And this is very similar to, this employs concepts of interferometry that you all are familiar with. You have all seen the Young's double slit experiment, and this experiment is basically very similar to that. So these are the earliest interferometry experiments, radio interferometry experiments carried out at Dover Heights in Australia. So these are the antennas that are kept on a high cliff, and the sea surface acts like a reflector. So from the source, you get direct radiation to the antenna and a reflected radiation from source to the sea surface, then to the antenna. So these two paths will create an interference pattern, which will give us some extra information about the source. And this is the experiment that we are going to replicate. Here is a example of how one can do this experiment. So you all have now a transmitter and a receiver, this kind of a system. So the source can be your, let's say, a mobile phone. We will substitute aluminum foil for the sea surface, and the receiver can be your laptop. So the laptop is at some height from this aluminum foil, and you will try to move this transmitter vertically from the bottom, and you will see the uh, effect of doing this on the received signal. So pictorically, this is how the setup will look like. So this is the transmitting source. It is at some height from this reflecting surface. Your receiver is also at some height. And so you will get a direct ray to the receiver, and there will be a reflected ray to the receiver. So both of these rays will interfere and create some interference pattern. So as you move your cell phone, you will get fringes. Basically, you will pass through maxima and minima and so on, and you will get that uh, power measured on the receiver. So the uh, the aim of this experiment is then to verify that the received signal or the received pattern matches what is expected in theory. And if it does not match, then can you figure out where things are different? So mathematically looking at this experiment, so this is basically very similar to Young's double slit experiment. So instead of transmitting through the two slits, we are receiving to the slits. So A and B, let us assume these are two antennas. They are separated by some distance 2h over here, 2 small h. And there is a source at infinity, a point source. So plane waves are coming to these two antennas. And these antennas are connected in such a way that we get some of these the field uh, at the receiver. So whatever field falls, electric field falls on this antenna, we get some of this field. So then you can see immediately that there is a phase difference here between the two rays coming to these two antennas, and this additional path length traveled by this second ray will introduce some phase which will create some interference. So as the source moves in the sky, so the we can treat these two signals. The antennas will basically convert these rays or waves coming to the antenna into some electrical signals. We can assume that well, these will be sinusoidal. For now, let us assume it's a simple case. These are sinusoidal signals. So we add them as phasors. So the signal at A has some amplitude and some frequency, and signal at B has some amplitude, and we are assuming it's same frequency. But there is a phase difference between these two signals, which is phi, which comes from this extra path traveled by the second signal. And this extra path is basically, you can see from the geometry, if theta is the uh, elevation angle of the source, then this is 2h sine theta, this extra path. And we can convert this into radians. We just divide this path by lambda and multiply it by 2 pi, and that gives us this phase phi between the two waves. So in phasor addition, it is very similar to vector addition. So if we if we add, then we get this equation. C square, which is the sum of these two waves, is basically a square plus b square plus 2ab cos phi. A and b are the amplitudes of the waves at the two antennas, and phi is this phase difference that we calculated here. So in reality, I mean, this is the full equation. But for if we want to simplify, if the source is at infinity and so on, then A and B, we can say that they have same peak amplitude. So we can say A square plus B, A square is equal to B square, which is some power P naught. A and B are amplitude, so their squares will be proportional to power. And C square is also the measured power. And then the equation simplifies to this form. If we substitute the phase that we calculated here, then we get this final equation. And this is the equation. As you vary this theta, the power measured will vary according to this equation. So you can see that it depends on the wavelength, of course. And another uh, component here is the separation between the two antennas. So if you increase the separation, these fringes should reduce. So this is, I mean, you all must have seen Young's double slit experiment. There also,
Fringes will be faster.
yeah, I can maybe, I have some animation here. Yeah. So this is the typical Young's double slit setup. You can, I mean, there is an added complication here. There is one more slit which creates these wavefronts. But for simplicity, you can assume that the wavefronts falling on these two slits are plane wavefronts. The principle here that I was talking about is if you reduce the distance between these two slits, the fringes will become wider and wider. And if you increase the distance, they will become narrower and narrower. So now by controlling this distance between these two slits, you can look at different sizes of sources. So a source which is very, very small, like a point source, will not affect any fringes. But if the source is very large, these fringes will start disappearing for some distances. So if we vary the distance between these two antennas, at some point this uh, fringes will start disappearing, and that's when you know that you are basically resolving the source. Yeah, so basically the waves coming from 2 points on the source are destructively interfering, and the interference pattern starts disappearing. So this is one way to get some idea of the angular size of the source. Uh, so yeah, so back to our case. Uh, so in our experiment, yeah, so this is the setup that we will have. So clearly there are immediately you can see that the the source is not at infinity for us. Our transmitter, the mobile phone, is very close to the receiver. So the angle subtended by these two rays will not be same. But we can still simplify the problem. We are only interested in the extra path that this second ray travels. So we construct an isosceles triangle and do the same exercise to find the extra path traveled by this second ray. And we find that extra path is over here, uh, given by this equation. So this is straightforward geometry. We use sine laws and cosine laws for triangles, and we get this equation. And in this case, the final equation for the received power is like this. So this is very similar to the previous equation, except for one negative sign. One negative sign here. Uh, can someone think why we got a negative sign here? I mean, sorry, the answer is given here. But yeah, so basically in our experiment, the second ray will go through a reflection from the surface, which introduces a phase difference of pi, and that gives a negative sign here. the phase here is 2 pi by lambda into L. L is this extra path length, and that is given by this equation. So L is slightly complicated here as compared to the previous equation. So this is the model that you have, and now you basically have to take measurements. So there are some uh, so there are some knowns, and there are some known quantities, and there are some measured quantities. So now here are in this L you see this angles beta and alpha are mentioned. So we don't know these angles, but these can be easily, we can get them easily from the known quantities. So capital H is the height of the transmitter from this reflecting surface. Small h is the height from the height of the receiver from the reflecting surface, and d is the distance between horizontal distance between the transmitter and the receiver. So to get alpha, you use this equation. It's basically simple trigonometry again. And to get beta, you basically again calculate the theta and then get beta here. So these are uh, from basically from known quantities. You can calculate alpha and beta, and then you can substitute them in this equation and get the value for P. So this is the expected plot. Yeah, here the difference is that this power must be converted to linear scale before fitting your model to this plot. And so this is the exercise that you are going to carry out. Again, this is an ideal setup. This is kept outside, outdoors on a rooftop, so there are no obstructions nearby. And so while taking measurements, make sure you are also not obstructing or moving around the setup. And again, if you don't have such kind of an arrangement for transmitter, you can just hold it in your hand and ask someone to measure, or you can time the measurements and then check on the plot. So that is the exercise that we are going to do in this experiment. Yeah, so any questions about this? Jameer, I won't be able to see the chat, so if there are questions, let me know.
Yeah, still I didn't get any questions in the chat box. So if there, I will let
Someone raised a hand.
you can unmute yourself and
Hello,
ask Shlok.
I'm audible.
Yeah, Shlok, go ahead.
Actually, I wanted to ask, can you again tell with what signal we have to compare our results?
With what signal? I mean,
Yeah,
no,
like the ideal one.
you will get some measurements as you move this transmitter. You will get some measurements, and you will have to compare it with this model. That does this agree with your measurement?
Okay, okay.
Yeah.
Understood.
And if there are any deviations, can you explain those deviations?
So we will already have this model in the detector.
No, this is all your mathematical exercise. The detector will just the receiver
Detector
will
will
just,
only measure the power, okay,
yeah.
which is a
Okay.
sum of the two signal voltages or fields added with whatever phase relationship they might have, and modular square of that sum is what you measure on your device, okay, measuring device. And its variation has to be seen as you move the transmitter height, okay, which is analogous to a source rising, okay, and changing in its elevation with respect to the sea surface, and an observer sitting at a constant place.
Yeah.
Thank you.
Yeah, there is a question. Yeah, transmitter should be kept isolated, or is it okay if we fix it in the wall? So definitely we can't fix in the wall, so we are avoiding walls. Okay, it should be somewhere suspended, or maybe you can like knot it to a stick, as Ashish has shown in the image. Okay, so that is the preferable. Ashish, you have any comment?
Yeah, so avoid any large obstructions nearby. That is, otherwise you will have a third reflection or a fourth reflection, and yeah, then this simple model would not be applicable. Yeah, although if one can try, what would happen if you have a third reflection and so on.
Yeah, there is a comment, or more like a comment. Let me read it from the chat. Vinisha has comment. This experiment seems to be very similar to the previous one. Absolutely right. In terms of the setup, we are using the same equipment largely. Instead of putting the reflector behind the radiator, we are now putting it horizontal. But in terms of resources used, it's very similar. It also uses the principle of reflection and interference, but it's a very different qualitative experiment. We had seen longitudinal interference. Now we are seeing in the transverse direction. Okay. And the previous one wouldn't improve your resolution. It will change, of course, the directivity of your antenna, which is, you can say, yes, it has changed the resolution in terms of the direction in which it is radiating more. But here, now we have a separation between them in the transverse direction. And that is what makes the difference in terms of giving you angular resolution, which improves orders of magnitude compared to the nominal gain we get of reduction of the pattern by a factor of 2 largely in the back reflector. So yes, there are lots of similarities. In fact, it's purposely done so that the same equipment, when configured differently, you can see it illustrates very different principles, and its effectiveness and usage are quite different. And this is a good example of that.
Yeah, so just to clarify, I think I did not mention the second antenna forms in the image plane. So this reflector uh, the reflector creates an image of the second antenna. So these two antennas are basically, uh, this is how we get the analogy of the Young's double slit experiment. And here also you can see the fringe, the angular size of the fringes that we get depends on this distance between the two antennas. So if the source is exactly in front of this setup, then the distance seen by the source between the antennas is 2h. But as the source keeps on rising, the source will see that the distance between the antennas is reducing. So the size of the fringe, or the angular size of the fringe, will change as the source moves through the sky. And there we can actually get different resolutions from the source. So in fact, the highest resolution, as you can see, we get when the source is very close to the horizon. And that was what people were trying to do here. They were trying to see sunspots and so on when the sun was just rising, because that would give the maximum resolution. And this they did confirm there was a large solar flare, and they observed some radio signature of the flare, and so that was a big discovery at that time. So yeah, these are early days of radio interferometry, but very significant results. So this basically led to our modern nowadays the interferometers that we use, like GMRT and so on. So these are precursory experiments to these modern interferometers.
Suppose we use two independent
Sorry.
mobiles.
Shafiq, there is echo. Okay. Yeah.
Yeah.
Go ahead.
Suppose we use two independent different mobile phones. Can they act as two different coherent sources? Can we demonstrate interference in that fashion?
Well,
You cannot unless they are at the same frequency.
yeah.
Yeah, suppose I am using the same identical mobiles, almost the same.
Yeah. If they are monochromatic, truly speaking, which they are not normally, they have finite bandwidth. And unless they are transmitting the same signal, you won't have the concept of coherence truly ensured. But if you somehow arrange for them to transmit the same thing, then of course they will lead to interference the way we see. Absolutely right.
So we tried actually this experiment, but with the receivers, and it turns out that as long as the two devices have different crystal oscillators, which basically
I'm saying everything else has to be same. The synchronous, but even if
unless
they shift, okay, it will come out as a shift in the interference. The beat frequency will come out. You may not have a way of measuring it, okay, because your integration times might be longer than the time scale of the beat frequency. I mean beat variations, beat oscillations. Okay. But in principle, because this is what actually happens. Okay, just to stretch this question further, when two observers are observing a celestial source sitting on the earth at two different locations, they are actually moving at different speeds with respect to the source direction because of their location, both in longitude and latitude. Okay, so you will get the signal sent by the source received as a different signal at the two places. And the trick is to restore the apparently lost coherence is by correcting for the frequencies by appropriately accounting for the motions of the receptors. And when you do that, you will see that you can restore the coherence. If there is mutual coherence to begin with, and you have not done anything to destroy it, then it can be recovered. So the local oscillator inside your mobile, which is not told to you about, might be a free running oscillator or oscillator which knows nothing about the oscillator in the other, and that will change the phase relationship between the two in a manner that will destroy the coherence.
Yeah. So this PPT will be shared with you. So yeah, you will have this mathematical models available to you, although they are not that difficult to derive.
So this figure might suddenly surprise you as the place where the D is. That is taken for taking this isosceles, triangle, so that one can easily calculate the extra length but the ray is not indicated by these two sides of the triangle. Okay. The first side, the ones emanating from C are correct rays, but the ray going to A after reflection will begin at the place where it meets the surface.
Yeah.
Okay, so that is the some dotted line you can draw to show that that is the real ray, and
Yeah.
it is by symmetry that is the same length as going to point B from that point, and that is how imagines that for an observer sitting at C, the A will appear, the ray going along CD will appear like a ray coming from direction B. And you can even add, so that stuff you have written, AC is equal to DC. Yeah. Very good. Any other comments, questions? So it will be good to take readings of the height of the transmitter and the power received at point A as a pair of measurements you require for different settings of the height without changing the height of the receiver.
Yeah.
Without the location of the reflector.
Yeah. So the only variable that you are playing with is the height of the transmitter. For one set of observation, do not change any other variables.
So basically alpha and beta will continue to change. Okay.
Yeah. So can we know some more interesting experiments like this? There is a question. Well, in radio interferometry, there are certainly several experiments, but going beyond this would require some extra equipment.
Yeah, if it's not bound by the constraints on the equipment you can employ, there are very interesting experiments. This will even include just taking your the low noise receiver blocks that you get on top of your at the focus of your satellite dishes. You could grab two of them and separate them looking up at the sky without using the dish surface, and point it to the sun or let the sun transit through across the the meridian, and you will get fringes. Radiation from the sun can be picked up, but the catch is, again, these low noise blocks will have a local oscillator. If you force the same local oscillator to be used in both of them, then the coherence will be retained and the interference will be seen. So you can do versions of this. You can vary the interferometer spacings. Actually, then use that to find out the size of the source, size of the sun, for example. Okay, and this is what people actually did early on. People actually used another version of this called intensity interferometry in optical, and measured by seeing how the correlation or the net power seen when you add these two or cross correlate these two will fall as a function of separation between the two telescopes. One could actually use that as a measure of sizes of those stars. This is how the early measurements of star sizes was done. And the person who employed that was Hanbury Brown. And of course, the idea of intensity interferometry. This is coherent interferometry. We're using actually voltages and fields. But when you have enough bandwidth, you can show that you will have coherence between the intensities received at the two locations also, based on the size of the source. So there is a very famous experiment, Hanbury-Brown Twiss interferometer, which you can you would already know about, but you can revisit the discussion there in the context of such experiments. You might find it the connections are pretty robust.
Yeah, there is a question. Can we increase the receiver's height above the transmitter?
Yes, you can.
Yeah, I mean, as long as you know this relation, how you're getting the transmitted and reflected rays. Yeah.
And you have a reflector at the place where the likely reflection, prominent reflection is going to occur. Okay. Then, of course, you can feel free to raise the point A from the symmetry plane. I just think of the geometry and where you would see. Of course, what is happening in reality is the reflection is not just one ray coming and getting reflected. It's the entire wavefront, and in this particular case, spherical wavefront. Okay, incident on the reflecting surface, and then getting translated. So all those complications will be there, and that will decide really what the net signal that is reaching point A after reflection, and with what phase description across the wavefront that is reaching point A post reflection. That will decide the net answer. But ray optics will be guiding enough for you to know where you should. Suppose you had a smaller piece of the reflector, to know where to keep it. That consideration will certainly come from knowing the heights of the receiver as well as the transmitter. And does it largely answer your question about the height of the receiver? Was that in the chat? Was that question in the chat? Probably a direct.
It was a direct message, I think.
Ah, okay. So maybe you can confirm by the direct response if the query has been answered or not. The analogous situation of your first experiment, you could actually use that while you are talking over your phone. Try putting a back reflector, right, and see whether it improves the reception. Of course, you don't want to be in the way, so you can put it on speaker and see if the signal level increases. Of course, the situation within a room while you're talking on the mobile phone is very different, because all kinds of reflections are really making a pattern of highs and lows across your room, not just across the floor dimension, but even in the vertical dimension. So that's a complicated situation. But wherever it is, still, if you were to use a reflector behind, it might help you to orient it in a proper direction so that your signal level can show a bit of increase. How much increase is not very clear in that situation. In the cleaner situation that we have described, of course, it's very easily predictable.
So it will be interesting to see results for this experiment. I mean, it involves several factors that you may have to account and so on. So yeah, let's hope everybody can perform the experiment. So I guess only extra important material required here is the aluminum foil. Yeah, which can be easily made available.
What you mean is a bigger aluminum foil, right? Because they must use that for the back reflector.
Yeah.
In any case, so they just need a bigger reflector along one dimension at least. There was a question in one of the direct questions was the measurement. Would it use the same software that they use for previous experiment? And the answer is yes, in case others also have similar question. You can also do since somebody asked, can you do other experiments? You can demonstrate inverse square law. One of the experiments like that is actually listed by us in the repository, which is not included here right now, just for keeping it less crowded. But you can do this experiment where you can move away from the radiator or move the radiator away, whichever way, as long as the distance between the two changes without having any complications of other reflections and so on. And you would see drop in the power received following the inverse square law. Inverse square of the distance. Are there any other questions, comments? Probably I don't see any. Do you see any?
Yeah, I don't have any direct questions. Yeah.
Jameer can probably.
No, I don't have any message or questions.
Okay, no hands raised.
Please do let us know if you have any query or doubts regarding this experiment or the pair experiment.
There is one query on the chat box. Let me see. Can different shape be used for reflector in this setup? Yes, in principle, but then of course you will get different results. depending on what that shape is and how does it change the property of the reflected wavefront. For any shape that you might use, it should be, at least crudely, you should be able to predict the way it would affect your measurements. So yes, in principle, you can. And of course, there could be some shapes where the reflection itself never allowed to reach the receiver, in which case you would see only the direct ray, and you won't see the interference. If the shape is such that it goes through multiple reflections and sometimes even reflected back to the radiator, then again you will have so whatever shape you would use, you can see the effect of it. As an extreme case of it, if you had undulations of this surface at the level of on the scales of the wavelength or good fraction of the wavelength, then you're making the reflection itself incoherent. You're disturbing the wavefront coherence within that reflection itself. And so it will, based on the different phase shifts that, because of the undulations that will be incorporated to different pieces of the wavefront, will show up in the way you will begin to lose the correlation. So that's also another experiment you can try. You can make patches sort of, or have some random locations, random pieces of it only reflecting, the others are not reflecting. You will find that, or shift them, at different heights, which can be simply, by crumbling the foil enough. But it has to be the crumbling, both in terms of its change in the extra path length, has to be of the order of the wavelength for it to show significantly in the change as a result of the interference. So for any shape you take, please make sure that you can work out from simple ray optics first the possibility of reflected ray ever even reaching the receiver. If that is ensured, then you can work out the rest of the piece details of the geometry to find out the phase difference. Feel free to try out variations on this. They will be instructive in any case. Does it answer your question, largely? I forget who had that question. Okay, Giriraj, question. Okay, thanks. You can also see the effect of or the role of the surface which is reflecting, which is playing the more prominent role, which part of it is playing more prominent role in the ranges of the heights that you have chosen. By removing reflector in certain piece parts and see if it affects your measurement significantly, or extending the reflector in the lateral direction, in the direction perpendicular to the line joining the two. See if that reflection was, which you have not receiving, would it have made big difference? And you will find that it may not make a big difference. that's why in the illustration you will see a reasonably narrow strip has been used, typically of the width of few lambda wavelengths. Any other comments? Okay, looks like there are no further comments as far as I can see. So thanks, Ashish, for.
Thank you all.
If there are no comments or questions, we can end the session.
Okay, if you face any problems in doing this experiment or any other questions that might come to your mind while doing the experiment or later while analyzing the data, feel free to post them in the form. We will take them up in the busy hour next week.
Thanks, Desh. Thanks, Ashish.
Okay, thank you, everyone. And probably we'll talk to you again weekly. Have a nice weekend, all of you.